How are we doing, guys? We are looking at page 22, exercise 2A from Fundamental Applied Maths. And there's the question, question 12. We're going to do it twice, and we are going to see it once where we treat P and Q separately, and once where we use a trick to make our lives a lot easier. Now, why are we doing it twice? Well, what we would like to learn from this is that while there are very often many ways that you can do a question in applied maths, a lot of the time there's an easiest way or a most efficient way. And really, if you study this stuff properly, you're going to save yourself a lot of work by learning some of these tricks and some of these easier approaches. So we're going to do it twice. You're told that you've got P and Q 162 meters apart. This body leaves P with initial speed 5 and travels towards Q with uniform acceleration of 3 meters per second. At the same time, this second body leaves Q with initial speed 7, a uniform acceleration of 2 meters per second. The question is, after how many seconds do they meet? And then what then is the speed of each body? So really what we want to say is, after how many seconds do they meet? The speed of each body we'll come back to later. Now, if we were to treat P and Q separately, you'll say, well, P has an initial velocity of 5 meters per second, an acceleration of 3, and it's been traveling for a time t. That's the time elapsed. Q has an initial velocity of 7. It's been accelerating at 2 meters per second squared and has also been traveling for a time t. And S is what we are interested in. Now, these are not the same. If P has traveled some distance S, then in that same time Q will have traveled, say, 162 meters, take away whatever that distance is. Okay, so that's going to give us two sets of equations. When we go to pick our equations, you'll go to page 50 in your log tables, look up mechanics, and you'll say, well, which one, we don't really use this one very often, which one of these three, V is what I'm not interested in, which one has no final velocity in it? And the one that has no final velocity in it is S equals ut plus a half at squared. So that's what we're going to use. S equals ut plus a half at squared. Well, for P, that is going to give us that the unknown distance here, and I'm going to call that just S, and I'm going to call this 162 minus S. Okay, and S in both cases means this distance here. And so for P, we'll get that distance traveled by P is initial velocity is 5 multiplied by t plus a half of the acceleration times t squared. Okay, whereas for Q, we're going to get that the initial velocity is 162 minus whatever that S is. And that's the same as 7t plus a half of twice the acceleration, t squared. Okay, so what we have now is two simultaneous equations in two unknowns. So we can solve this. We can solve this for t, and we're going to get ourselves a quadratic in doing it. Okay, but it's a hard thing to do. There's a lot of algebra in it. So I'm going to jump through that algebra very quickly and tell you not to worry about it, because when we see our second method, we're not going to have to do this. So how do you solve two simultaneous equations? You can subtract them if they're linear. These are not. These are a quadratic element because there's a t squared. So you substitute this S in here. You get 162 minus, instead of that S, you say you get this S here. 5t plus a half of 3t squared. And that equals 7t plus a half of 2t squared. And I'm going to run through that very, very quickly, but don't worry if you don't follow it. Okay, so removing the brackets makes it minus and minus, and then a half of 3 is 1.5, a half of 2 is 1. The next thing I've done is moved these three terms over to the right-hand side. So I get 0 equals 7t plus t squared, but now it's minus 5t, plus 5t plus 1.5t squared, and minus 162 because I've moved them over to the far side. Now, I should have said earlier, I don't need you to take down this algebra, okay? So don't worry about getting this down. See if you can follow it. All I've done here is said 1.5 plus 1 makes 2.5t squared. 5t and 7t makes 12t, and minus 162 stays as it is. Then I'm going to multiply through by 2 so that I don't have this decimal just because it's a bit untidy. Okay, so here's our quadratic in t. Bit of a mess. We need to solve that using minus b. Okay, so if we're solving that, then a is 5, b is 24, and c is negative 324. Don't forget that negative sign, and then plug it into your quadratic formula. Okay, hopefully you know your quadratic formula off by heart. There it is, minus b plus minus b squared, root b squared minus 4ac, all over 2a. Again, it's in the log tables if you don't, but that's something you need to have committed to memory. You're going to see it a lot. I always say fill it in with empty brackets. Okay, so A is 5, that goes here. B is 24, that goes there, and it goes there. And, oh, sorry, A goes down there, 5 as well, and C is minus 324. Okay, so that minus there is important because you get minus times a minus makes a plus. Okay, and when you do the calculator work on that, you get minus 24, 576 is 24 squared, 6,480. Add them together, take the square root, you get 84. So minus 24 plus or minus 84 over 10. And ultimately you get two answers, minus 10.8 or plus 6 seconds. And that's the correct answer there. Negative answers in time we ignore generally. We might discuss them in class. But just look at all the work in that, okay? The quadratic, by the way, is unavoidable. I think that's going to come up in this question anyway. But this substitution and all of this algebra, while you've done this question correctly, you've picked a kind of a long approach to it. So it's good to be able to pick the shorter approaches if you know them. Nothing wrong with this, and sometimes you do just need to grind through the maths. But better if you can find a faster way to do it. So what we're going to do instead is freeze Q in place. And we're going to say, well, how does P see Q move? Or how does Q, excuse me, see P moving? Okay, so if we come back to our old diagram, well, if P is initially moving towards Q at 5 meters per second, and Q is moving towards P at 7 meters per second, then Q will perceive that Q is really coming towards it at 12 meters per second, okay? It thinks, geez, this guy is really flying at me because it has its speed and his speed is the combined speed. That's called the relative speed, okay? So that's the speed of P relative to Q is 12 meters per second. You do the same thing with the acceleration, okay? P is speeding up. If you think of Q as being frozen in space, it sees P moving towards it with both the 3 meters per second that P is accelerating plus the 2 meters per second that Q is accelerating. So that's a relative acceleration of 5 meters per second squared. Okay, so using this relative approach, it's going to simplify the maths a lot. Okay, so because Q is not moving, really we're saying, well, if P starts at 12 meters per second and accelerates at 5 meters per second squared, how long will it take it to cover 162 meters worth of distance? So find T. So you're back again using S equals UT plus a half AT squared. Okay, same as you used before, because again, you're not interested in V. But this time it's 162 equals 12T plus a half of 5T squared. Now, you still have a quadratic, but this is going to be a lot tidier than the last one. So that's 162 is 12T plus 2.5T squared. Move that 162 over, and you get 2.5T squared plus 12T minus 162. And then I'm going to again just double that because it makes my life a little bit easier to not have the 2.5. So I get 5T squared plus 24T minus, what was that, 324. If you look there, that's the same equation that we had earlier. Okay, but I think it's been easier to get there. You still then need to go and use minus b, which I'm not going to do again. Okay, but there's question 12. All right, we'll leave it there. Sorry, your answer should be 6. You can try that yourselves if you like. Okay, and I'll leave it there.